Okay, so hi, I'm Rich Tuffin. I guess to start the theme, I got involved in tech, programming my dad's ZX Spectrum in BASIC. I wrote my first hacking tool, password brute forcer, on an ARM2 that ran at 8 megahertz and had 2 megabytes of RAM. And I've been working professionally in cybersecurity for about 20 years now, which is a bit scary. But I've never actually presented in public, so every day's a learning day. So I've been with Velexity for about 2 years, and we specialise in cybersecurity products and services built around memory analysis and memory forensics. And I started getting involved in a lot of cases involving edge devices, which is kind of handy because I used to be a vulnerability researcher working on edge devices. And I found there's not a lot of public information on how you apply memory analysis techniques to these kind of systems. So I thought, well, that's a good opportunity. I'll turn up at B-Sides and present on how you can do that. So what am I going to do? I'll start just by introducing why edge device security is a problem, talk a bit about why memory analysis can help you with that. We'll talk about how we collect memory on edge devices.
Sorry, I was further late. What is an edge device?
I'll explain that in a second, don't worry. How you can analyse memory from edge devices, talk about a couple of practical examples, and then I'm standing between you and lunch, but there should be time for questions at the end. So what do I mean by an edge device? So some kind of self-contained virtual or physical device that performs a particular network function. So a really common example, the box that your internet service provider sends you, you plug it in, it produces Wi-Fi. Good example of an edge device, sits between the internet and your network. A lot of corporate versions of these things these days you can also get as virtual devices. They run as virtual machines either in the public cloud or on your enterprise, but do very similar things. They filter traffic, they inspect traffic, they load balance across your website, lots of different things. They usually have some kind of custom web app or command line for management, and you buy these things as a black box. You don't go digging underneath, you don't really update them, you don't look at the operating system that's underneath. You just read the manual, configure it, work with it. Historically, when I started looking at these things, a lot of them ran proprietary real-time operating systems because they were operating on network packets. They need to be really fast. Processors weren't that fast at the time. You needed every millisecond you could get. These days, most of them run Linux. Not all, but almost all of these kind of systems run Linux. So why do they run Linux? One of the main reasons is vendors want to run on off-the-shelf physical and virtual hardware. So if you want a virtual device that runs in Amazon's cloud, Microsoft's cloud, on-premise virtual machines, easiest thing to do is to run Linux because all that compatibility is built in. And a lot of these vendors don't build their own hardware. They buy off-the-shelf standard server hardware systems, put a snazzy front panel on the front, put whatever accelerator cards they want in the back, and sell it to you, so they can just run on commodity hardware. But if you do have some kind of proprietary feature, so you want to implement some snazzy VPN, or you've got some AI accelerator card and you need a driver for it, the advantage of Linux is it's open, there's quite a pool of engineers who can develop that for you, all quite easy. And the final reason is it's low cost. So the actual technology itself is obviously open source and free, and you can buy or get open source toolkits that do a lot of the hard work of how do I package it up, how do I turn it into updates, how do I add other packages, all that kind of thing is kind of done for you. So it reduces the cost to companies of kind of putting this thing out to the market, because they want to be a load balancer or a snazzy AI data loss prevention tool. They don't really want to worry about all the underlying, how do I get network packets out. So what are the problems with edge devices? Well, they're often exposed to the internet by design. A VPN that doesn't let your employees connect from the internet is a fairly useless VPN. The standard, oh, well, I'll just not expose it, doesn't really work for a lot of these devices. They're supposed to be accessible from everywhere. They're not always the most secure of devices, and one thing that I've often talked about over the years, just because it's a security device, because it's a web application firewall, because it's trying to make your organisation more secure, does not necessarily mean that device itself is secure and well built, particularly the management web interfaces. So most of the vulnerabilities you see in these kind of things are in the management web interfaces that you use to manage and administer the box. Those were never intended to be put on the internet. but people do all the time. They're really attractive environments for attackers. So not only is it the initial point of entry, but it's often a place that lots of really interesting traffic goes. You can see all of the VPN traffic. You can mess with that VPN traffic. You might see all of your customer website traffic. You can put interesting things in that traffic. You might be scripting your HTTPS to your website, so all of a sudden you can see lots of credit card details. Lovely places to be. And because underneath this is a Linux box, all my standard tools work. If I want a socket forwarder, or I want some tool to capture data, I can just go grab an open source tool. I probably don't even need to compile it. It'll just work. With these older historical proprietary RTOSes, you have to do loads and loads of work to figure out how to run your own code. Really lowers the bar to entry. And they often lack the observability tools that we have on like standard servers and endpoints. So you don't have any antivirus, you don't have any EDR, and you've got really limited logging and inspection, just what the vendor chooses to give you. So what's the impact? Okay, so you've got potentially open door to your systems that's really difficult to monitor, that's really difficult to inspect, and is a great place for attackers to cause trouble. So if you follow the cybersecurity press, you've probably seen a whole load of examples about this. I'm deliberately not going to pick out any vendor in particular. This is an industry-wide problem. Pretty much all of the major vendors at some point in the last couple of years have had a fairly significant vulnerability, a fairly significant campaign of people actually exploiting these for real and using them to cause pain for companies and organisations. Okay, so that's the problem. How can memory analysis help? So first off, let me be clear kind of what I mean by memory analysis. So I say capture the state of the system by making a copy of physical memory. My kids are 4 and 7 and ask what do I do for a living, and I say I help people take crime scene photos of computers. I take a very accurate, very sharp picture of the state of that computer at the time, and then I help people dig through that photo with a magnifying glass and work out what's gone on that machine. So yeah, use analysis tools to capture and understand what's happening, what processes are running, what network connections are open, what files are open, and also what's happened in the past. So what's in the memory of your machine now is not just what's happening now, but also vestiges of what's happened recently. So network collections that have just closed, files that you read that are still hanging around in the cache, command history. Most shells will keep your history and they'll keep that in memory. And logs. Even if the logs haven't been pushed to disk, chances are they're hanging around in memory. So why do we want memory analysis on edge devices? Well, because they often have a very limited ability to inspect them. It's whatever the vendor gives you. The vendor will probably give you a few commands. They might give you some nice little pictures in the web interface that says, yeah, it's all fine, the CPU's fine, we're not using much memory, it's all great. But you can't dig right down to say, okay, what exactly are the Linux processes that are running on there? And are they supposed to be there? Vendors just don't want to give that to you. The other thing is they often run very largely in memory. So whereas with a traditional Linux server, you might be pushing quite a lot of stuff to disk. Things like swap files, things like hibernation files, things like a lot of detailed logging. Very often with these edge devices, they boot up out of a compressed firmware image, and then everything is in memory. And if that system gets rebooted, it's gone. You've got whatever the vendor chooses to log, which is typically not an awful lot. So we really like the same kind of gold standard memory analysis we get on standard Linux, Windows and Mac OS systems. We want a really in-depth understanding of what the attacker's done on this system. We want to be able to triage really quickly. So one of the nice things about memory analysis is you can very quickly include or exclude a system and say, yes, I'm pretty confident from what I can see, nothing malicious has happened here, let's move on. And it's also quite difficult for attackers to disable or evade. So one of the things you'll commonly see with edge device compromises is the first thing they do is they turn off logging, they disable your ability to take whatever the vendor's got for kind of providing information, and then you're pretty blind. Being able to defeat a full memory capture and completely hide from that is pretty tricky. You usually leave some kind of trace that an analyst can go and follow and find. So I'm going to talk today about Volatility 3, so probably the leading open source memory forensics framework, written in Python, runs on the command line, plugin based, fully open source, supported by a US foundation, the Volatility Foundation. Lots of powerful analysis plugins for macOS, Windows and Linux. There's lots of training, presentations, resources. I should say I mostly professionally focus on the kind of capture side of things. I use Volatility 3 a bit to kind of prove that what I've done is correct, but there are lots of resources out there. I've highlighted the Foundation website and the Foundation's GitHub as kind of good places to start if you want to know more about Volatility 3. Okay, so how do I go about collecting memory on an edge device? What do you need? So you've basically got three options. The first one is if you can get privileged access to the device, so the ability to download your own binary, run it, and thereby collect physical memory. Not all devices allow that, so some of these edge devices will give you essentially a root prompt if you type the right commands in the right sequence and ask it nicely and say yes, you promise not to break anything. But not all do. Some vendors lock that down and don't give access. The second option is that the vendor has privileged access. So for some vendors, if you open a tech support case with them, they can remote into the box, they can run a privileged process, and they can capture memory for you. Not all vendors will do that. Which vendors will do it seems to depend a little bit on who you are, when it is, what's going on. And it does require giving the vendor access to your device, which, depending on what the device is and where it's running, you may or may not be comfortable with. And the final option, which actually I've been surprised how often this is useful, is to take a memory snapshot. So if you're running a virtual appliance rather than a physical appliance, you can ask the hypervisor, so be it Proxmox, VMware, Microsoft Hyper-V, whatever, to take a snapshot of that machine for you. That will include all physical memory, and that's a really useful analysis technique. It obviously only works if it's running as a virtual machine, and unfortunately none of the public cloud platforms I'm aware of have this functionality, so this is private cloud only. Okay, so collection tools. So I should probably say, like, we as a company produce a collection tool. This is B-sides, it's not a sales pitch. There are lots of commercial and open source tools available for memory collection. They all use one of two approaches. One is to load their own Linux kernel module. So that requires that you have enough files about that specific system to be able to compile a kernel module. And it requires that you've got enough privileges to be able to load that kernel module, and that should then dump the memory for you. The second option is to use a Linux kernel feature called proc-kcore. This is intended to be able to attach kernel debuggers. Most desktop and server Linux distributions enable this, and actually a surprising number of edge devices, if you can get in, have this enabled. So generally, if you can get privileged, by which I mean root, really, access, at least one of those approaches will work. And if you kind of go through the set of tools that are available, if you can get that privileged access, usually you can collect memory. So that kind of gives us a grid. So depending on where is it running and what access have I got to the device, generally I can collect memory. What happens if I end up in the two red boxes here? So I've got a device where it's physical and the vendor is not letting me run my collection tools, or what I've done in the bottom right hand corner, so I can't run the collection tools, and I'm in public cloud, so I can't ask the hypervisor for a snapshot. Well, if you're in the middle of an incident, you haven't really got an option, you have to move on. But if it's your network, you can choose to change vendor. If it's your network, oh, jumped too far, you can change platform. So actually, if you're thinking about this up front and thinking, how would I do forensics in an incident, you can help yourself in the architecture. So if you've got appliances you know are high risk, you can choose to move them and go, actually, I'd improve my forensic posture if I use this different product that does this, give me this capability, or I run the same product, but actually I'll migrate it into our on-premises instances rather than running it in public cloud. Otherwise, you just have to use the best information you've got to triage it. and often end up replacing a box that you're not sure if it's compromised or not because there's nothing else you can do. Okay, so we've got lucky, we've got a vendor who supports collecting memory, we've managed to collect it, we've got a massive great memory dump. What do I do now? Well, doing memory analysis requires two things. The first is it requires what I always refer to as types. So this is what's the structure of kernel data. So a task struct, for example, on Linux describes a process. So what's the process called, what files does it go open, all of those things is all in a big C struct that you can go and inspect. You need to know what that looks like, and you need to know what that looks like on that particular device. And the other thing you need to know is symbols. Where is the data? So it's no use knowing what the data is without knowing where it is. So, for example, on Linux, init task describes the very first process that has started on a Linux system, and from there you can walk the list and the tree of all of the processes and find every process that's running. But if you don't know where that first process is, then you can't start that process. You need both of these for useful analysis, and I'll show why that's a problem. So I want something simple. I want to know the name of my process. So if I have the right structure, I have all the right offsets, it's all in the right place, but the symbol's wrong, then I put that over my memory capture and it's in the wrong place. And I think the process is called some nonsense because I'm just reading the wrong bit of memory. So that's no use. Okay, so I get the right symbol, so I'm in the right place, I found the right init task, but I've got the type wrong. The structure is a different size, there are some extra fields, the fields are in a different order. Again, get gobbledygook. So I have to get both of those things right. So just worth saying how symbols and types are handled in Volatility 3. So it uses something called an intermediate symbol format, which is just a big JSON file. There's a utility called dwarf2JSON that generates those from dwarf debug data. I'll talk a bit more about that in a sec. You need an accurate ISF. And Volatility 3 matches up images you've taken with the ISF you need via Linux Banner, which is a piece of data compiled into every Linux kernel. It's available via proc version if you're running a Linux system, and it's this big long string of gobbledygook that if you work in memory analysis, you get very familiar with very quickly. We'll talk about that a bit more in a sec. So where can I get symbols for edge devices? So really the best source of data for this is dwarf debug data. So when you compile a kernel, by default, as long as you've got the right options turned on, you'll also generate lots and lots of debug information. So that's really detailed information you can give to a debugger like GDB or LDB, so it knows what all the types are, where all those structures are, what all the parameters of function are, loads and loads of stuff. For a typical kernel, that's hundreds and hundreds of megabytes. So most vendors won't ship that with the actual kernel that you boot. They put it in a separate set of files. And for normal Linux distributions, you can download that file separately and then you've got all that information. You can use dwarf2JSON, use Volatility 3, life is good. You very rarely get these for edge devices. Vendors are very, very reluctant to give these to you because they perceive it as their proprietary information. It gives you lots of understanding about how their device works. Yeah, they don't like showing them. So the second source of symbols you can use is a text file called system.map. And if you've ever looked around in a Linux system, you might have seen this hanging around in /boot. And it's just a text file of addresses and symbols, and it's used for various kind of translation things so that when you get an error, it tells you what function failed rather than some address. It's surprising how often vendors ship this. There's no real use in them doing it, it's just that by default, if you use standard Linux utilities, you end up with this file on the file system. So you often find if you go onto a system, you can pull this off, and that gives you a source of symbols. And then the final one is most modern Linux kernels actually have a copy of the symbol table. So a list of all the functions and globals, their name and their address, encoded inside the kernel itself. And that's used for lots of different things like runtime instrumentation, things like producing nice error reports. There's a file in proc that will let you read them all back out again. So in most cases, the symbols you want are usually embedded in the kernel that you're actually running. And there are open source tools available that will just read those out for you. So in a lot of circumstances, yeah, you're good. One hiccup, which we'll see in one of the examples I've got later, sometimes that can just be functions, i.e. the code, and any globals are missing. But there are ways around that. We'll talk about that later. Okay, so that's symbols. I can find out where things are. Types. How do I find what everything is? Well, if I've got dwarf debug data, I'm good, but we've said we don't often get that. That sucks. If you have the kernels you need to compile kernel modules, then that can be helpful. It contains a lot of the types you want, and it was the default for the old Volatility 2 framework, but quite a lot's missing, and it's quite tricky to do. They're also not often available for edge devices, although you can actually, sometimes you can get them from the source code, which I'll talk about a bit more later. I don't really like working with these. It's my kind of method of last resort. And then another cool kind of technology, which is a whole talk in its own right, is extended Berkeley packet filter. So this is a really cool runtime instrumentation framework. But for what we're talking about today, it means that all of the kernel structures are embedded in a really compressed format in your bootable kernel image. So if this is turned on, you've got all the information you need in the kernel you're actually running. Sadly, either vendors are running kernels that are too old and don't have this feature, or they deliberately turn it off because they don't need it. So I've never seen an edge device that has useful BCF in. Maybe one day. Okay, so, but this is all open source. Can't we just build a new kernel with the debugger data in it? Right, GPL, I should have source code, should be good. And modern compilers are supposed to be deterministic and reproducible. So if I provide exactly the same input to a modern compiler, it should produce exactly the same output, byte for byte. Should be good. But same input means precisely the same input. So I need exactly the same kernel config, I need exactly the same source, I need exactly the same compiler, and in a lot of circumstances, I need exactly the same system state. So the file system layout can make enough difference in a kernel compilation that a kernel that you compiled and the kernel that I compiled won't match. Things will be at different places. So this is often feasible for types. The structures will be the same. I have very rarely managed to do this for symbols because one byte off, you cascade out, and all of a sudden your init task, the start of where all your processes come from, is somewhere completely different. So this sounds great, but it's largely useless. So this is a technique that I use instead. Donor kernels. So most modern Linux kernels have enough symbol data to do useful analysis, as I mentioned earlier. A kernel built from similar source and config should give you the same structures. Join the two things together, and you can produce an ISF that is actually useful, gives you usable analysis. So what do we need for input? We need a config. A lot of kernels embed that in the actual kernel itself. You can often find them on the file system. I'm not sure why vendors do that, but they often do. If you ask the vendor for their GPL source, they'll often include the config. You can reverse engineer the config out. I'll talk more about that at the end if we've got time. You need the same source. So if you're lucky, they're using some public source, so something that the kernel developers have published on kernel.org or some other Linux distro. It ought to be available via GPL compliance. I'll talk more about that in a sec. And you can sometimes work out what changes the vendor's made via reverse engineering. For same toolchain, usually same GCC version is fine. And likewise, the build system, if all you want is some matching types, doesn't really matter. Yeah, so GPL compliance. So Linux kernel is GPL v2. You must make sure that they too receive or can get the source code. Great, problem solved. There are three typical ways that vendors comply with this. One is they publish it for everybody to see online. That's great, that's easy, download it, great. The other is they publish the source for customers to access, and that might well mean you're paying several £1,000s for a support license for that particular product before you can get to that. That also gets tricky in situations like I encounter where I don't have a license to the product, my customer has a license to the product, and that communication can get quite tricky. And the most annoying one that is entirely legal, they provide an email address or a postal address. Please send a check for $15 to this US address, and at some point we will post you back a CD containing the source code you've asked for. Requests for source can take a long time to process. I think my record is well over a year. If you're working on incident response where you're talking hours and days, that is essentially useless. The publicly available source doesn't always actually match what's running on the device. Companies aren't always brilliant about keeping that up to date. And it might not contain everything you need. So they don't necessarily include the kernel config. They don't necessarily check that it actually works and you can actually compile it. Yeah, it's annoying. What can you do? If it's your device, you can ask for the GPL source code well before you need it. If you know what you're running, you can go and do that, kick that process off before you're in the middle of an incident. I tend to hoard source code. Even if it's not exactly the right code, often it comes in handy. But yeah, if you own your devices, getting hold of the source code is a really good idea. You can often use the nearest available public source. A lot of vendors don't actually change their kernel; they don't actually care. It is going to fall over if the vendor has made some kind of proprietary change. And as I said earlier, you can reverse engineer it. It is time consuming. Okay, so that's kind of the theory of it. Let's put this into practice. Well, I'm not using real examples here. A couple of reasons. One is client confidentiality. We work on breaches that often end up in the press, but we don't necessarily talk about the role, and that takes quite some time. So it's easy not to do that. And I wanted to focus on the techniques, not on can you do this on vendor X or vendor Y, because that changes over time. It depends exactly which product you're talking about. And the final thing is, although the kernel is GPL, usually all of the stuff that's running on top of it is proprietary, and you click on EULAs when you download it to say, yes, I'm not going to share this. This is B-sides, I think it should be about learning, so everything here you can recreate using publicly available, openly licensed content. But they're all based on techniques that I've used for real. So, hi Rich, working on an urgent incident response coming across a B-sides OS 1 device that we think might be involved in the initial compromise. Being able to collect memory, we need an ICF. Can you help? Looks like this is the banner. Let's break that down. So this is an x86 64 kernel, and it's running kernel version 6.12.0. It's got a big line of gobbledygook in the middle, which tells me that it's some Linux distribution, and they're supporting this for a long period of time, so they've released a whole series of patches. One of the things that the kernel includes is what was the user and what was the host that it was built on, and very often that's helpful. Rocky Linux are particularly helpful in the they put their actual domain of their actual build hosts in there. So this is Rocky Linux, that's cool. And it was built using GCC 14.3 with a set of patches that Red Hat maintain. If you've not come across Rocky Linux, it's a rebuild of Red Hat's operating system, so that kind of makes sense. And it has a timestamp in it, so it was likely built on Tuesday, November the 11th. That is almost always the case. Okay, so you figured that out. Apply years of experience or Google search engine of your choice. You can usually track down what is this, where does it come from. So in this case, this is a public kernel, and Rocky Linux make all of their debug symbols available publicly if you download, and that's great. So I can match up. You'll see here that times don't quite match. So that says November 13th, that says November 11th. That's fine. What's happened is they've compiled the kernel, they've done some testing, and at some point a couple of days later they've put the package together and put it up on their website. Yeah. Okay, so download the package, extract it, run the dwarf to JSON, analyze it, send it off. Thanks. We can't see any malicious activity on that system, we'll keep looking. And this is one of the cool things about memory analysis. If you've got all that really in-depth understanding of what's been running, what we've seen on it, you can very quickly go, nah, wrong place, let's move on. That's really valuable. But things are never that easy, and usually on a Friday night, because a lot of people I work with in the US. We've just got another B-sides capture from the customer. Looks like this is version 2. Can't find a matching kernel for this one. Could you take a look? Here's the banner in the kernel. Okay, and I've highlighted a couple of bits. Okay, so this is 6.12.81-B-sides OS. I'm guessing I'm not going to find this on Google anywhere. So what are we going to do about that? So the version number says 6.12.81. with a custom version string. It was compiled by bsides build at bsidesosbuild.internal, so probably something to do with the conference. Still compile on Rocky Linux. And if we go and run, there's a script in the Linux kernel source called extract ikconfig. That gives me the kernel config, so that tells me how they configured it. So that was nice of somebody. So one thing the kernel developers do is take a particular kernel release and support it for a couple of years. They're called long-term releases. And a lot of vendors will use these long-term releases because it means that they don't have to keep changing things. The Linux kernel loves reorganizing things. Vendors don't generally love having to keep up with that. So they'll typically pick a long-term support version and then use it for very long periods of time. So yeah, hopefully that is somewhere close. So how do we build a donor kernel? Go grab the source, grab the kernel config, build the donor, and then we've got what we need for an ISF. So we grab the symbols that we need. So I mentioned earlier VM Linux to ELF. That comes with a tool called KAllSyms Finder that will pull out all of those symbol addresses. And then I usually just use a little Python script to turn that into the system.map format that we saw earlier. I do actually have a patch for the tool to do it. I should probably upstream it. Build the ISF, and this is where we Frankenstein the two things together. So we take the types from our donor that we've just built, and we use the symbols from the system map that we've just read out of the kernel. We update the Linux banner to match. So I said Volatility 3 uses the banner to match up the ISF and the actual kernel you're analysing. So to make sure it's got the right one, you have to do a bit of JSON munging using whatever tool you prefer for JSON munging to make that match. Analyse. Cool. Okay, so I should probably show you some analysis. So yeah, apparently they're very busy, so let's do some analysis. So lots of people use volatility in lots of different ways. I like starting with PS tree. So this gives you a process tree. So starting with init, the sort of first parent process, what spawned what's the parent-child relationship all the way down. So this is SSHD, calls a couple of SSHD sessions, calls bash, calls a couple of sudo, calls bash again. Oh, that looks kind of interesting. This is actually me logging into memory capture. I need root access to be able to access proc kcore and read memory. So what you're seeing here is me logging into the box via SSH and capturing the memory that lets me do this analysis. Okay, so that's not so interesting. So let's look further down the PS tree. Okay, so why is there a Python 3 process and a bash process owned by init? So this is called demonization, so it means these have been unlinked from whatever they were started with and connected to init, so they're never going to die. You wouldn't normally expect to see a scripting program connected to init, and you certainly wouldn't normally expect to see a bash process. Normally it would be the parent of, be the child of SSH as we saw, or like something normal. Okay, so let's switch to a different plugin. Let's call SockStat, so that this lets me see active network connections. So why is that bash process connecting its standard in and out to a network socket? That's a bit weird. Okay, so let's use the bash plugin. So this lets me pull out the bash history out of the bash process, even if it hasn't been written to disk anywhere. So that's cool. Okay, so at that timestamp there, they ran ID, and at that timestamp right there, they ran echo, hi there, besides extra. Okay. So, kind of show you what's behind the curtain. So my demo system has a web server that has a by design command injection. I send some data to a particular URL, it'll run whatever command I ask it to. Not that different from quite a lot of edge device vulnerabilities, sadly. I use that to start a reverse shell that connected back to my system, and then I typed a couple of commands, ID and echo, to check that was all working. So that just lets you see, it's a toy example, but how you can very quickly go from the memory dump to what was going on in this system and kind of pull on the threads to find out what was going on. Okay, thanks, we managed to pivot from those IPs, but we can't figure this one out. And you have a quick look, and as I mentioned earlier, there's no data symbols. It's quite common for edge device symbols, for edge device kernels to be compiled with no data symbols. This config KAllSyms all is not set. Vendors think you don't need them, there's no particular use for them, they drop them. That's terrible for us doing memory analysis because pretty much everything we want to know is a global in the kernel somewhere. So init task, where the process is, that's a global, it's a data symbol. If it's missing, we're in trouble. So I promised in my abstract that we do some reverse engineering. So let's do some reverse engineering. So who here's played with Ghidra? Some of you, cool. Open source reverse engineering tool developed by NSA on GitHub, lots of powerful stuff. We're just going to talk about version tracking. This is a feature that is intended to let you port analysis from one version to the next. So if I've done lots of analysis on version 1, the company comes out with version 2, I don't lose all of that, I can copy it. We're going to use it in a slightly different way. There's lots of information on the training that's built into every Ghidra release, if you're interested. So version tracking has this feature called implied matches. It's very simple. If function 1 and function 2 both reference a global in the first version, and function 1 and function 2 reference the same global in the second version, obviously that's the case. In reality, it's more complicated because there's lots and lots of globals and lots of functions, and they can conflict and all these things. But at a toy level, that's all we need to do. So if I look at some decompilation, so on the left-hand side here, I've got my donor, which has got the symbols that I want. On the right-hand side is the one that I'm analysing, and it hasn't. It's got, they're missing. So I can start up a version tracking session. I can match up the function names, because I know those. And then down at the bottom, you'll see there's this implied matches. And so you can see it's found those two data symbols we want, and the source is filled in, and the right-hand side isn't filled in. If I press a couple of buttons, I can fill it in on the right-hand side. And I do that about 60 times, depending on how many functions how many plugins you want to run, and you're there. So here's the workflow. So we build a donor as before. We use version tracking to recover the data symbols. That is automatable via scripting. You can click through the GUI if you want, if you're learning. But yeah, you can script it all. You generate system.map from the recovered addresses. I just use a Ghidra script again to write out that really simple system map format. And then exactly as we've done before, build a donor ISF, analyze, and we're good. Yeah, done our analysis, help save the world, go home. Yeah, I've got a couple of minutes. So there are a few more advanced problems. If you don't have a config, it is possible to infer it via reverse engineering. So Linux kernel flags will turn particular functions off so they don't get included, so you can tell whether a particular flag is on or off by whether those functions exist. You can also start digging down into functions and go, is it accessing this data structure or not? Oh, okay, that must mean that that config flag is there or not. It takes a long time. Vendor-specific kernel modifications I mentioned before, they're quite common, particularly for network appliance vendors. They're very time-consuming, but it is possible to reverse engineer them. And if you don't have any function symbols at all, I've never actually seen this in practice. It is theoretically possible. I think you could use version tracking. I wouldn't want to do it, and I certainly wouldn't want to do it under time pressure. So there we go. Memory analysis can be powerful. Requires quite a bit of additional effort compared to doing it on standard systems. It's often, but not always, possible to collect and analyse. It's hugely useful if you can, and it's much easier to prepare in advance. So find out what your vendor offers, get the kernel source, understand the collection options, and actually go through a test collection before you've got a live incident. Yeah, and then if you take nothing else away from this presentation, reduce the attack surface of your edge device. If it's a management web interface, it's on the internet, take it off the internet. It's much better to avoid an incident than to do lots of funky memory analysis to work out what happened after the event. Yeah, and then my contact details are there. We're lunch is next, I think, but happy to take questions.
Do you have a vendor you'd like to work with, and have you worked with any consumer devices?
So consumer devices, no, because we tend to work with enterprise clients and they tend to be running larger devices. I won't comment on the vendor stuff with the cameras rolling, if that's all right.
Okay. Last relay. A little bit earlier, we talked about like an ideal system where you would like have access to all these things. So I'm just wondering, like, would this ideal system be easier to exploit because attackers would have all these tools as well?
So it is a balance. So like giving the access to allow you to take memory captures, yeah, does require additional access to the system. If you're doing this really well, you design it so that that is a very limited set of access. So like if I were designing it, you'd make sure that only specific processes could access the mechanisms you need. So there are tools built in, like SE6, to let you do that. So you can keep it locked down while also giving the visibility, but it is something you need to think about.
Yeah, business question really. Do you provide consulting on the preparation side so that a company can be confident they can get memory from devices, all the devices possible?
As part of other services, yes. Probably worth a longer chat afterwards, but yeah.
From the memory acquisition side of things, is there like a public list available that tells you what kind of vendors support the acquisition of memory, so that it also puts pressure on the vendors, or to at least increase the level of transparency, so companies or enterprises that are thinking of purchasing these products know the limitations? Is there something already out there from a documentation point of view?
No, not really. I didn't put it in here partly because it's a moving target. So, you know, people watching back on the YouTube, it wouldn't be the same in 3 months, 6 months' time. There's a lot of pressure from organisations like NCSC for vendors to do more in this space. But no, there isn't at the moment a really good way of telling.
It's a hot
which
topic.
vendors support
I mean,
which.
I think yesterday there was even something again to China Nexus on edge devices.
Mhm.
So I'm still very surprised that we are then, from a defender side of point, trying to catch up, and we still even have the capabilities to catch up because vendors are preventing us.
I think my experience is it's hard enough to get companies to put a security check into the purchasing process, let alone we want to be able to do some fancy debugging after we bought it.
Yeah, sure.
Yeah, it's only one element of lots of choices you've got to make, and you don't always get to pick.
Yeah, so in the event that you have one of these devices where you can't like get root to like take a memory capture, to the best of my knowledge, most of these devices are built not dissimilarly to like a normal computer. There are like a lot of, for like mostly for cheating at video games, like hardware memory tampering devices.
Yeah.
Could you potentially install one of those in your edge computer in order to like allow you to take a memory capture even though you can't get in like on the operating system?
Yeah, so in theory, yeah. So I didn't include it in this because very few companies are going to be comfortable with you installing a piece of hardware and certainly invalidates your warranty. But yes, in principle, like if you can use PCI Leech or one of those similar technologies to read out of memory and you're prepared to take, then that is a technique that would work. Yeah, it has obvious challenges if you want to run supportable IT. So.
I'm afraid we have run out of time, but please give it up for the speaker.